So whenever a fluid flows past a body, or when a body flows past a fluid, there is a resistance offered by the fluid on the body, and this is basically because of the formation of boundary layer. So in this particular unit we are going to study about this boundary layer. So whenever the ship or submarine is flowing in the sea, or when the aircraft is flying in the air, there is formation of this boundary layer on the body of the aircraft or on the body of the submarine. So this boundary layer consideration is very important while designing of aircraft or submarines, because this is basically responsible for the drag force, and this, if not considered properly, it will lead you to disaster. Now we will understand what actually is this boundary layer. So suppose we have this flat surface and the stream of air is flowing over this. Now what will happen? So the stream of air which is in contact with this flat surface will have zero velocity, will have the velocity as that of the flat surface, because flat surface is at rest, so it will have the zero velocity. Now what about the stream which is in the stream of air which is in just in contact with the first layer? The first layer obviously will have zero velocity. The second layer which is in contact with the first layer will have certain velocity. Now because of viscosity property of the fluid, the bottommost layer will resist the flow, and obviously it will have certain velocity. Now the layer above this layer will have some more velocity. The layer above this layer will have some more velocity. In this way we have the velocity gradient. So you can see here the velocity is increasing as we are moving in transverse direction, and finally after a certain point the velocity becomes equal to that of the free stream velocity, which is u infinity we are considering. Or if the velocity is even 0.99 of u infinity, then also we consider it as equal to the u infinity. Okay, so in this, at this particular point we have seen the velocity profile which is like this. Okay, now moving further, at this point, moving in the direction of flow at this particular point, now what will happen? So here again we will have the same velocity profile qualitatively but not quantitatively, because now in the same layer the velocity will be less, because more and more fluid comes in contact from here, and because of friction that energy will lose, and therefore the because the kinetic energy is lost, so the velocity will be now less. So in the same layer, if I compare these two, the velocity will be less in this particular point, at this particular point as compared to this point. Okay, so obviously the velocity profile will be same. Here the velocity is increasing again same in the same manner as it was increasing in the first point. Okay, and after a certain point we will have the velocity equal to that of the u infinity. Okay, but that point, the height of that point will be more as compared to the height which we got in this point, because the velocity here is less, so it will take more distance to cover to attain the same velocity which is that of the free stream velocity. Getting this or not? Okay, similarly if I move further, at this particular point again I have same velocity profile, but the velocity in same layer will be less, and the velocity profile will be up to more distance, more transverse distance than as compared to first and second point. Getting this thing or not? Okay, so if I join the locus of all the points, the point up to which we are getting the velocity gradient, because after this point the velocity is constant and we are getting a straight curve. So at this particular point we are getting, up to this particular point we are getting the velocity gradient. Here up to this particular point we are getting velocity gradient, here up to this particular point we are getting velocity gradient. So if I join the locus of all these points, I will get one layer, and this layer is nothing but the boundary layer. Okay, and this boundary layer is actually the concept. This is not you cannot see the boundary layer in reality, this is just the concept. Okay, a concept which is made in order to explain you what actually is the effect of the flat surface on the free stream velocity. Okay, so this actually signifies, this actually tells us the up to which level the effect of this flat surface will be there in the free stream velocity, because after this particular boundary layer we will have the free stream velocity. Getting this or not? Okay. Now the distance of this flat surface up to the boundary layer is nothing but the boundary layer thickness, which we denote by del. Okay, so as you can see, the boundary layer thickness is 0 in the leading edge, and it is maximum at the trailing edge, and it keeps on increasing from leading edge to trailing edge. Now what are the effect of free stream velocity and viscosity of fluid on this boundary layer thickness? So as the velocity of the fluid is more, there will be less time for viscous force to act, and therefore this boundary layer thickness will be less. More is the velocity of the fluid, less will be the boundary layer thickness. Okay, what about viscosity? More is the viscosity, obviously more resistance will be there, and since more resistance is there, so the boundary layer thickness will be more. Now up to some region from this leading edge, we will have the laminar flow. Laminar flow means the flow will be streamlined and will be parallel to that of the flat surface. Now after a point, the flow will become unstable. That point is known as the point of transition, and after which we have a transition zone, and after transition zone we will have the turbulent flow. That means the layers of the fluid will intermix with each other and the flow will be turbulent. Okay, so we have three different regions. First is of laminar boundary layer, second is of transition boundary layer, and third is of turbulent boundary layer. Okay, in this turbulent boundary layer also we have a small sub layer which is called as the laminar sublayer, because the layer of fluid which are near to this flat surface, even though they are in turbulent zone, but near to this flat surface they will have less velocity. Okay, so in turbulent zone also we will have a sub layer which is called as the laminar sub layer, and above this boundary layer obviously the flow can be either laminar or turbulent depending upon the free stream velocity. Okay, now the flow inside boundary layer is laminar or turbulent or transition. It depends on the Reynolds number. Reynolds number obviously we know is rho v L by mu, or you can say v into L by nu. Okay, here v is nothing but the free stream velocity, which is u infinity. L is taken as the distance from the leading edge, okay, which is taken here as x. The L is replaced by x, where x is the distance from the leading edge, and nu is the dynamic viscosity. So Reynolds number will be equal to u infinity into x by nu. Okay, now if this Reynolds number is less than 3 into 10 raised power 5, the flow is laminar. If this Reynolds number lies between 3 into 10 raised power 5 to 5 into 10 raised power 5, the flow will be transition, and if this Reynolds number is greater than 5 into 10 raised power 5, the flow will be turbulent. Now in laminar region, as we are moving towards the flow, the velocity gradient becomes less and less steep, because as I told you, in this at the same surface the velocities becomes less. Okay, so the steepness of velocity will be less as compared to that of the edges which are near to the leading edge. Okay, so as we are proceeding towards the flow in the laminar region, the velocity gradient becomes less and less steep. Now what about in turbulent region? So in turbulent region, because there is intermixing of layers, so there is lot of exchange of momentum between the layers. Okay, so obviously the velocity gradient will be more. So velocity gradient for this turbulent layer is more as compared to that of in laminar layer. So you can see a graph between y by del and u by u infinity, and you can see here the turbulent steepness, the steepness of the turbulent flow is more as compared to that of the laminar flow. More in the sense, more you have to see with respect to y axis, not with respect to x axis. Don't get confused with this. When I am saying more steepness, that more steepness, because we are considering the velocity gradient in y direction, so the more steepness is taken with respect to y axis and not the x. Now what about the shear stress acting on this plate? So the shear stress acting on this plate will decrease because the velocity gradient is getting less and less steeper, and we know tau is directly proportional to du by dy. So as the velocity gradient in laminar region is decreasing in the direction of flow, so the wall shear stress of this plate will decrease in the direction of flow for the laminar region. Okay, now in turbulent region, as the velocity gradient is increasing, obviously the wall shear stress will also increase. Getting this or not? Okay, so you can see the graph of this wall shear stress tau naught with respect to distance from the leading edge, and you can see in laminar region the shear stress is decreasing, wall shear stress is decreasing up to transition zone, and after that the wall shear stress increases continuously.
So we can conclude all these important points from this boundary layer theory. First, the boundary layer thickness del is taken to be distance from the plate surface to a point where velocity u is equal to 0.99 of u infinity. The thickness of boundary layer is variable along the flow direction with 0 at leading edge, which increases towards trailing edge. For high incoming velocity, there would be less time for viscous force to act and hence less quantum of boundary layer thickness at the particular distance from the leading edge. For fluid with high kinematic viscosity, boundary layer thickness is greater. For some distance from leading edge, boundary layer is laminar, flow is smooth and streamlined. Subsequently, laminar boundary layer becomes unstable from a point called transition point. Flow is transition flow. After going through transition zone of finite length, boundary layer entirely changes to turbulent boundary layer. Underlying turbulent boundary layer, an extremely thin layer called laminar sublayer is formed, wherein flow is essentially of laminar character. Outside boundary layer, main fluid flow may be either laminar or turbulent. Reynolds number Re is equal to x into u infinity by nu, where x is the distance from leading edge of the plate. If Re is less than 3 into 10 raised to power 5, flow is laminar. If Re lies between 3 into 10 raised to power 5 to 5 into 10 raised to power 5, flow is transition. And if Re is greater than 5 into 10 raised to power 5, then it is turbulent flow. In laminar boundary layer, velocity gradient becomes less steep as we proceed along flow. Turbulent boundary layer has much steeper velocity gradient at the plate surface when compared to those for the laminar boundary layer. Velocity gradient and shear stress has higher value at plate surface. For laminar boundary layer, the velocity gradient becomes smaller along the flow direction, and so does the shear stress. For turbulent boundary layer, the shear stress at the plate surface again takes up high value consistent with steeper velocity gradient.